three of them. And then the other thing is because some people were starting to ask me about possible thesis work in this area. Yeah, there's a lot of work that needs to be done with AI, in particular relating to wargaming, and my interests go well beyond that. I mean, I think it needs to have a big impact in the analysis area as well, operational planning, a lot of places where I want to see it have impact, and I'm not the only one who thinks it should be having impact there. But the technology ripens on its own schedule, you know. And for right now, what I could say is that wargaming is definitely is the easiest. As hard as it is, it's really hard to support wargaming with tech. As you know, we're going to have some seminars about this in the spring, so stay tuned if you're interested in that. Uh, but we want to do it, and AI is just one part of that. But I want to make sure the AI is the best possible and the best in the world. I don't see why it can't be for wargaming. We don't have a whole lot of competition out there specifically for wargaming. So for those of you who are possibly headed to McWill or MCU, I guess at least one person will go to MCU. So you're like prime candidates as far as I'm concerned. If you want, now you can do your thesis for what you want. Let me preface this. I'll give you the professor view of this. I don't see that you absolutely have to connect your thesis to your work when you go out in the field, but there are big advantages to doing that. You'll go out there spun up better. You'll be able to reach back easier to help us influence because you'll realize the problems, and you'll also be an expert in some part of those problems. And then you can kind of consult with myself and with other people here to say, hey, we really need people to do a thesis on this topic or this topic. These are issues where that could really have an impact. Now, I've always had great relationships with our alums, but we've never really gotten a chain where we can develop tech here and really push it out to the fleet in a meaningful way, just because the tech hasn't been mature enough. And I feel like we're right on the cusp now, and this is the first year I'm really pushing to try to see what we can do in that area. And so that's already more than I thought I was going to say about that. But maybe I'll say even a little more. I'll steal a little time from a lecture soon, maybe this week, just to kind of give you the lay of the land the way I see it, for those of you who might be interested in that stuff. And yeah, hopefully that's of some broader general interest as well. I won't belabor it too much in case it's not. All right. All right. Okay, so today we are finally ready to talk about Lab 2. So I don't think Lab 2 has the greatest material to ramp up on, so I think we may actually have to read some code this time. But hopefully, if you see online, you should see Lab 2 is open in Sakai. The assignment's there. It's set to be due a week from today. I would recommend that if it's all the same to you and your schedule allows it, try to be done by the Friday before, just because I might have to brief the next lab that Friday. So it'd be nicer just mentally. If it was me, I'd rather have one lab closed before I have to start thinking about the next one. And I don't think that's unreasonable given the nature of this lab. It's not trivial, but I give you a pretty good starting point. So without further ado, so the main thing you're going to pull down is this lab2.zip. So there it is in my directory. That's what I pushed up to the server. So hopefully that's going to be exactly what you see. And when you unpack it, you will see a bunch of source files, an assignment, and also one slide of prep, which I think is not quite enough. So we'll try to elaborate on that a little bit today. Okay, so first things first, I like to start with the assignment because, again, that's really what you have to do. You can maybe find a shorter path to a good product than I can think of. So let's get the hard constraints out of the way first. So here we are. This is Lab 2. So we talked about neural nets. And what I've said, which is just a claim at this point for you guys, unless you happen to know about neural nets from other sources, that, whatever they look like they're doing, learning language models, classifying images, under the hood, they are function learners. They take X's and Y's and they learn given the X's to predict the Y's. That's always kind of that's what neural networks are good for. And that's basically what they're doing under the hood. Okay. And then it's creativity, riffing on top of that and using the neural networks as a module within a bigger system that allows us to do the language modeling, the image processing, what have you. Okay. So for this week, we want to focus in for this lab, we want to focus in on that core functionality, make it as simple as remove as many distractions as I can. So we won't be doing anything too sexy. I mean, learning a function is not very sexy. Okay, I would admit that. But unless you're a statistician, in which case you love that stuff. So no insults to those folks, but it's not all that sexy for anyone else. But it's it's a way to leave everything else extraneous to the side and really focus in on core issues that are always going to be there, no matter what cool stuff you might do with a neural net in the future. Okay. All right. So what we're going to do is we have a function y equals x, which I'm not telling you what that function is. I'm not giving you code to represent that function. All I'm giving you are samples, and the samples are noisy. Okay. So you get x, y data, right? Given a model of f for x drawn from the same distribution as our xy data, we want to be able to estimate y as accurately as possible, right? Again, we don't just want to learn the data I give you. The goal is to learn any data that comes from that same source. Okay, there's got some language in there which is maybe a little bit interesting. There's a little like lawyerese in here that the samples are drawn, the X values need to be drawn from the same distribution as our data. Like, what's that about? Right? I mean, if you've got a function, we know functions can be defined. Most of the basic ones in math are defined from negative infinity to positive infinity, right? No one has a data set that covers that range, right? We always cover some finite range. Okay. And if I only give you data for positive values of X, and I say, well, but I'd like you to learn something that works for all values of X, that's not very reasonable. Okay. And that's generally not the task. Okay. The task is, okay, I drew from some distribution, and that distribution told me maybe it was, whatever it is, uniform, Gaussian, whatever. It gave me the X's. Then I applied the function to the Y to get a pure Y value. And then, because this is a classroom example, I added noise, right? If you're doing sonar data, right, the X's were determined by how you decided to set your independent variables, right? What were the C conditions that day? What was the range from the object? All that kind of stuff. That's what determined the X's, okay? And then the Y's and the noise were inseparable for the field data. And in my case, because it's a Blackboard problem, I add the noise in manually. Okay? Is it clear enough? Okay. At the end of the day, though, it's not reasonable to expect you to be able to handle a different part of the x-axis than you actually had data. Okay. All right. So let's see. So you want to be able to estimate y as accurately as possible. Okay, great. And that's defined here as the lowest average squared error, which I've already led on to you is that's not the only way to cut things. And especially when you have a lot of noise, people have found that maybe use the absolute value instead of the square or even some more exotic things. That's maybe more of an issue for the stats folks. Okay. And our question is, what is the best model of F possible in the form of a single hidden layer neural network of ReLU units? Okay. So that is like the picture that I drew, right? The signals come in. I had a layer of input units, which I told you is just a way of drawing the fact that the signal comes in, but it's split and it goes to every neuron that needs to see it. That's all that first layer was. Then we had a second layer, okay, which is getting all those inputs, okay? And in our case, the activation function, the function that is on the output of the neural network is a ReLU, okay? And then there is an output layer. which in our case, because we're doing function regression here, that output neuron is going to be a linear neuron. If we were doing classification or representing a probability distribution, as we might for a large language model, for example, or for an image classification problem, that output unit would probably not be a linear unit. It would probably be a logistic, or it would be probably a sigmoidal unit, sigmoidal shape. Probably not ReLU though, either. Okay, output units are kind of special. We pick them to suit our problem. All right. All right, so you understand what the question is. All right. So this is actually very constrained. I mean, we only have I can tell you there's only one Y value. So it's one input dimension. There's X is one dimensional and Y is one dimensional. So that means how many output units will we have? One. Okay, and how many input units will we have? One. And that leaves the only question for the architecture of the net is, well, the architecture is kind of fixed, so to speak. If the architecture is the topology, how things are connected, that's fixed. Okay, but the only question about the net at all is just how many hidden units do you actually want to have? Okay.
Do you mind if we change that parameter at all, or you want to?
Oh no, you got to change it. Yeah, I mean, yeah. So when you guys give me your neural networks, you all do the best you can. And then I will measure them on data that you haven't seen, which seems unfair, but that's the whole point of it. It's the whole point of this exercise.
What I'm saying is that line right there says what is the best model of that possible in the form of a single hidden layer neural network. So we can't add more hidden layers.
Oh yeah, no, you shouldn't add more hidden layers. Yeah, so sorry, I didn't hear your question properly. My bad. Okay. Okay, but the width of that hidden layer for sure you want to play with. Okay. Now what are the pros and cons there? If my width is really, really tiny, what problem am I likely to have? What if I put one hidden unit?
It's going to be a pretty linear output. Not going to get very hidden.
And it's going to look just like a ReLU, in fact. Yeah, because what else could it be? It's going to be a ReLU that goes through a linear scaling. Okay. Well, if our function actually happens to look like that, we'll be good. And if not, we'll be screwed. Okay, so that's the issue there. How about if should I just start off with just 1 million? Because you probably can run 1 million, probably can run quite a bit more than that. Hidden units?
It's probably overfitting.
Overfitting, it becomes the problem at that point. Yep. And then you'll fool yourself, possibly, into thinking you have a better answer than you have. But hopefully you won't fool yourself either, because you'll have a held out data set and you'll know things are not going well before you turn your thing in. All right. All right. Okay, so you're going to provide your answer in the form of a directory containing your best model, which the code I give you already, when it creates a model, it puts it into a directory. So that's what I'm talking about there. With a lab report describing your work. Now, if you want to make multiple models, which you probably will, because you'll be playing them off against one another. If you want to actually turn in those models, I don't mind, but please make clear which one you say is your single unique best one in your estimation. That'll be the one I focus on. So I would like to see some example plots of training set error versus training time, hopefully shows that you were near a local minimum when the run was stopped, unless you're doing what's in the extra credit here somewhere. I should be, yes, down here, way down here. Okay, so you want to be sure you got near a local minimum, and even if you didn't, anyway, document how you did, right? So your training set error should be going down, 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 and we expect that it should have been leveled off pretty well by the time you turn the thing off. That's what I'm talking about here. Okay. All right. Let's see. In the report, comment on the errors you measure on the training set as compared to the data not trained on. Yeah, you'll have both training set and held out set. Is it true that training set error is usually an optimistic estimate of future performance, as far as you can see? Usually is. Maybe shouldn't have been in that sentence because you'll only have a limited number of examples, but Yeah, that was the claim, right? That you're liable to be too optimistic about what you think and do. Tell me what you actually see. Okay. Comment on overfitting. Okay. Did you observe any? If you did, then how did you try to mitigate it? So you could limit the number of hidden units, right? You could do weight decay, which we haven't talked about the algorithm for that yet in class, but it's real easy. Well, in the next real lecture, we'll talk about that. It'll take us 10 minutes. It's not a lot, or possibly early stopping, but that requires no implementation. That's kind of optional. Anyway, if you were able to mitigate it, tell me how you did it. All right. Okay, any questions? That's like the actual assignment. So any questions so far? Okay. And hints and other stuff. Okay, yeah. You should really try to train till the local minimum is reached. That's good form, and it's good to show evidence that this is the case, at least to me. Asking for it. You may adjust the learning rate, the run duration in epochs, and one epoch, I don't think we've used that term yet in class, but if you've got a data set, one pass through the data set is an epoch. Okay. If you're doing true gradient descent, where every time you take a step, you go through the entire data set, then I guess each step is going to be an epoch. Okay. But that's not normally what we do. Normally, we're taking one sample at a time. We're shuffling the data set and doing one sample at a time. But when you get all the way to the end of your shuffled set, that's one epoch. That's just a convenient unit for how much training you're doing. Okay. Right. So you can vary the run duration in epochs. Um, Vary the number of units in the hidden layers we talked about and the amount of weight decay. Okay, we did talk about weight decay qualitatively. I'll just remind you what that is. So weight decay kind of encourages weights to be as small as possible, right? And like anything else you can do. I mean, if you have a function or a parameterized function that's actually a family of functions and you're using them to fit data, any constraint you put on that to say that, oh no, you can't use these values, or I'm going to discourage you from using these types of values, removes the flexibility from that set of function. Okay, and therefore can help with overtraining. So that's kind of the intuitive idea. So if you have a weight decay of 0, that means you're not doing any of that. If the weight decay ramps up, then you're doing at least some. That's maybe enough for the lab. Use the training data to train each network and the held back data to decide which is best. Okay, fair enough. Okay, so what's suggested here is a more liberal use of the held back data than I indicated was optimal in the lecture notes, right? And I'll stand by what's in the lecture notes. If you really need a serious, non-biased estimate of future performance, then you really just want to use that special data that estimates that one time. A minimum number of times. But here, our purpose is a little different. Our purpose is not to get that. I'm not saying I'm going to grade you on how accurate you predict that. Maybe I should be great. Maybe I should ask you to put a stake in the ground and say, I think I can get this squared error. But I'm not asking for that. I'm just asking for the best neural network that you think we have. Okay. So because of that, we can be a little more liberal in how we use the held out data. Okay. Again, so I'm trying to have some kind of option in here. So that's the code's all there. So just in case you would like to use your programming chops to do something meaningful, one of my favorite methods, maybe my absolute favorite method for dealing with overfitting is the early stopping method, which we talked about. So for that, that's not in the code, so that would take some thought, maybe a tiny bit of research, maybe a bit of programming to actually make that happen. But it's a nice technique, right? And I like that because it's kind of win-win. So the way it avoids overgeneralization is by stopping early, which saves computation. So I'm like, those are two of the big problems when you're training a neural network. Generalizing, and I don't have enough computation, so it seems to help in both areas. So, hey, what's not to like? Yeah. So then you're going to need to split it. You're going to need to give up some of your training data. So that might be painful and might affect your performance too. So, so I don't know. Maybe this won't be your best neural network if you actually do this. And then, yeah, so I haven't. So the best implementations of early stopping have a patience parameter, which you could look for online to see what that is. And it's basically just, I'll tell you just in a few words what that is, right? The general idea is that we're training on this data, epoch after epoch, and then looking at a special set of data that's only used for this kind of technique, which we allow ourselves to peek at however many times we want to see what our performance is. And the idea is once the performance on the training data should be going down forever. Okay. But the performance on that set will not be going down forever. It'll go down to a certain point and then it will start coming back up again. Okay. And if you just immediately stop as soon as you see that it went up, then that would be like a patience of 1. Okay. But you might say, this application seems to be a bit noisy just because it went up one time. I don't believe that it's done with productive learning. I actually think it should go up more than that. Then you could have a bigger patience. A patience of 9 would mean it's going to have to go up like 9 times in a row before you go and say, time to stop. Yeah, patience of 9 is kind of really a lot. But patience of 2 or 3 instead of 1, I could easily believe you could get a better result like that. Okay. I mean, that's totally optional. That would just be extra credit in case you want to do a little more that involves programming. Okay. All right. So what the code that I'm giving you is set up to easily let you do is vary the learning rate, which could be any positive number. Learning rate is that eta, right? You get the gradient, we multiply it by that eta. That's that parameter. So it's almost always less than 1. That's not a written in stone anywhere, but usually you start off with a tenth or a hundredth or something like that as an initial stab, but then you might get smart about it and realize that, oh, that's too small. You'd like it to be as big as possible such that you still get good results, right? Because that will mean larger steps and getting to the solution quicker. Okay, but if it's too big, then you end up with that non-convergence, instability, all that ugly stuff. All right. Okay, epochs, right? So how many epochs of training do you want to do? Again, early stopping is its own thing, but if you're not doing early stopping, it makes sense to just have epochs be a fixed number that you decide in advance. Hey, train for 1,000 epochs, 1,000 passes through the data. The number of units could be any positive integer. Weight decay could be 0 or any positive float, but usually a small positive float. Again, of order 1 or less, I think. Typically, if I remember right, I haven't messed with it for a while. Okay, now you can mess with, aside from the extra credit, you can mess with the code any way you want. Make your life easy. It's just there to help you. So there are at least 3 files of significance, and there's actually a 4th. This is the one you use to train networks. There's one that generates plots, so you can actually see how you're doing against your training data or your held out data. And this also tests against some held out data, but just gives you the number, the average squared error number. Okay. And that's it. Any questions? So far, so good. All right. Now, the other thing that's in there, and it's very brief, but there is where's it? It's not there. Fine. It's a PDF. Here it is. All right, so there's just one slide in this tiny deck, okay, and just gives you some guidance to get going. Assuming you're going to work on Hamming again for this whole quarter, there's almost nothing that I think there literally is nothing where you really if you've got a decent laptop, you don't have to use it, but I do recommend it just because it removes friction. Because come summer, when all of a sudden you want to jump in Hamming, if you're used to that and you've been through the pain again and again and again with lab 1 and lab 2 and on, then it's going to be no big deal to switch over to Hamming. And otherwise, I think Otherwise, I don't think you'll have that as a tool because no one needs it's already stressful enough to start in on a new lab. And if I start in on a new lab plus do it a way you've never done before, jumping onto hamming that's probably a bit much for anybody. Okay. All right. So anyway, so let's say we're going to work on hamming. Then that lab2.zip, would want to move that over to hamming. This is, if you remember, I gave a bunch of example tools you could use to move it. Like, I don't know, like people on Mac OS, maybe you'll be using SE. That SCP is like a secure copy, but it's fine to do it any way you want. I'm going to do it on MOBA for right now. So let me just kind of jump in there and jump online. Okay. My directory. Okay. And now I want to move up that lab2.zip if I can find it. Here it is. Open. Okay. And then you see it transferring over on the lower left, and now it should be there. Let's see. Yep, it's there. Okay. What's next? Assumes you're logged in hamming, typing in, okay, fine. Make a work directory, put your files, unpack your files where you want to put them by saying unzip. Okay, and in my case, I have a subdirectory for this class already there. You may as well. MV to move lab2.zip to that directory. Okay, now let's go in the directory ourselves and do the unzip thing. You'll see I've got some old files there. There's a subdirectory, but other than that, nothing's there. Okay, there we go. And these files, again, the PDF is there, which doesn't help me, and the assignment doesn't help me there either, but the PY files you need for the lab are there, and these pickle files are the data.
Can you run a file on him?
No, it shouldn't. Yeah, it's supposed to be portable. Let's take a look. Great question. Let's look at the pickle. Let's look at pickle. If we, okay, actually, before I do that, let me just go over some other stuff, which maybe you don't need, but so generally, if you're actually going to do stuff on hamming, they don't want you to do it on the submission node that you're connected to when you first log in. They want you to be on a computation node, and this is how you ask for computation node. You can say more than that, and you will in the summer to ask for, I need one with this much memory, and I need one with a GPU for what I'm going to do. You can ask for all that by a more complicated incantation. Okay, but I'm going to worry about that for now. No, not what I wanted. All right, there it is. srun pty minus pty bash is the shell. Boom. And you'll notice I was on a submit node. Now I'm on one of the compute nodes. Okay, now I just don't have to worry about it. I can do what I want. All right, now the next thing is, okay, so this you might have already done, or I don't think we talked about Conda in previous labs, right? So this is an optional thing, but it's such a good tool. I use it constantly. I certainly use it in the summer, so you could probably get away with not using it. But what Conda is about is it basically makes these sandboxed Python environments for you. That, as you'll notice, like I feel like for this lab, I recommend Python 3.9, which is a little bit old of a version of Python. That's probably not what you would just have if you just go and install modern Python. But and this lets me make a sandbox that has like a little bit stale version of Python because some of the software I want to use kind of requires it. Okay. And then later in the day, if I'm get some shiny new code off the web and I want to mess with it with Python 3.12 or something like that, no problem. I can create another sandbox and say, give me 3.12. Okay. And furthermore, it's more detailed than that. It's not even just, I don't want to make it sound like it's just the Python version because it can be stuff like PyTorch is a main neural network tool. You might be doing stuff. Some of you have gone off and done stuff with PyTorch, for other activities on campus. Okay. And they might want to use PyTorch version X, whereas I might want you to use PyTorch version Y. Well, how do you deal with that? Same thing. If you can make a sandbox with Conda and have all the right versions of everything you want to use for that particular project loaded in there. Okay, so it's a great tool. And this is how you would create an environment with a particular version of Python. I've already done that, so I'm not actually going to execute that. If you do that and it complains that you don't have Conda, should be a way. Huh. That's so funny. Let me. This is an old version of that file. I'm afraid I gave you the older version. Well. Okay. Oh, sorry about that. It's not missing a lot, but it is missing one specific thing. So if you go Conda and it's like, what's Conda? Okay. That means that you need to do something like this. Module load lang / mini Conda, blah, 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 blah. Okay, there's a nice module system that's available there. And just in general, if you want to use some software on Hamming and it's not in your environment, you try using it and you see it's not there, okay, you can do, let's see, module avail for available and just get kind of pages of stuff that's already there. Okay, among that, in that list there somewhere is all kinds of versions of Python and also mini Conda, which is a version of Conda that I like. Okay, all right, so if you do module load, then you'll have Conda. If you do an invocation like this, name it whatever you want to name it, you will then create your sandbox. Okay, then the next thing you need to do is if you've got multiple sandbox, I mean, when you go onto Hamming, how does it know which one you want to use? So then you do something like this. Conda, activate, and your environment name to turn one of the sandboxes on, so to speak. Put yourself in that sandbox. Okay. If you want this to happen every time if you get tired of typing that and you want this to happen every time you log in, you can do this invocation, which basically puts this command into a file, which bash, which is your shell, which I'm running in the console, is hard coded to look for that file and execute all the commands in it before any new session which you create. Okay. All right. All right. And then to get your PyTorch in and a bunch of other stuff, which we maybe need for lab 3, you can just do this. Pip install this, and if that will take a while. It's going to pull stuff from the web. It's all automated. It should be fine. Okay. And once it's done, you should be ready to go. Okay. And then you can work interactively on a compute node. Okay. Or if you really want to run stuff and then walk away, then you remember from lab 0, hopefully. You need to make a little .sh file, a shell file with like a couple lines in it. It's real easy. Go look at the lab 0 brief and see what the pattern is, and voila, you should be good. Any questions about this? All right, now I'm going to just go and now that I've said that, now I can go and let's take a look at the pickle stuff. Okay, so if I just run Python, so pickling, what is pickle? You guys know pickle from summer? So pickling is a way it's basically, it's like a zip. It's like an archiving or compression program that can go and take make a big data much smaller so it loads faster or it's easier to move across the web. And it's used all the time. And in particular for this data I gave you is pickled. So if you just kind of go and like put it in an editor or whatever, it'll be a bunch of gobbledygook. That's all compressed. Okay, so in Python, this is how you can mess with it. And the files I gave you already know this. Okay, but just to give you a tiny example to see how you do it. So pickle is its own thing. So you got to pull it in like that, and then you need to open the file. So say file is open, and then the file name, which I think is train.pkl, train.pickle, and then you've probably opened files before, but you might not have used a second argument. So this is necessary when there's anything funny going on here. R stands for I'm going to read the file, which that's nothing funny. But B is, and it's a binary file. So open it like a binary file needs to be opened. That is funny. And so you've got to do that to make it work right. Okay, so now I've got my file object that has the data. I still can't see any data. So then what you do is you decide what variable name, my variable, wherever you want that data to live, okay? And then you go pickle, load, and then the file. Okay, so if I just do my variable here, okay, so this is what that data looks like, which is kind of a mess. Okay. Um, so but I can see it's an array. Okay, so let's just look at the first element of that data. Okay, so what does that look like? X and the corresponding Y. Okay, and now from here, if you're like, well, I don't want the data in pickle form, I want to do some other stuff with it. Okay, we just add a few lines to Python and have it spit it out in a normal, text form, and then you can do what you want with it. Okay. All right. All right. So the programs that I'm giving you. So there's this program called train.py. So this is intended to train your system, and it won't run unless you give it some arguments. So you have to give it the training file name. That's the data name, train.pickle in our case. Okay, the number of hidden units you want it to use, the weight decay parameter you want, the learning rate you want it to use, the number of epochs you want it to run, and then optionally, that's the square braces, where do you want to put it? If you're going to be building model after model after model and comparing them and turning in the best one, you might want to use that parameter to tell it where you want to put it. If you don't, it will just make a directory called modeldir and put the results there. If I go Python, let's see, train.py. Okay, train.pickle is the data file. Let's do the simplest possible thing. One hidden unit. See if the output really does look like a ReLU. I've never actually done it for real. This will kind of be interesting. Let's say no weight decay. Let's say something small for the learning rate. I mean, you're guessing to start out with. Okay. Number of epochs. I know 100 is like nothing for this thing. So let's go 1,000. Okay. Now you'll see while it runs, that's it. It just trained for 1,000 epochs. Every 100, it goes and prints out the sum of squares of error. And what do we see here? This is a very typical pattern. A lot of times it gets stuck right away, but not always. Yeah. Welcome to the world of stochastic engineering. That's the world we live in. If you're building a neural net, you're doing stochastic engineering. You can do everything right and get an unlucky initial set of weights or parameters and not maybe get the best result. Let's do it again. Let's see how consistent it is. It's going to complain about the modeldir, though. Let me first kill the old modeldir. Remove recursively and force. So don't do this unless you mean it. It won't. The F means don't prompt me and ask if I really want to delete stuff. I really want to delete stuff. Okay. Okay. Now the old model's gone. Let's do it again. So we have 0.6102. Wow, we got like the same answer. Look at that. Like the very beginning was different. You'll notice it wasn't the right at the beginning. This is way worse than the other one was. And then looks like it got sucked to the exact same local minimum, which is interesting. You don't always see that. Let's try again. Now look, I forgot to kill the old model directory. Okay, my bad. But you notice we got quite a bit better this time. Like 5% better, something like that. That's significant. Okay. All right. And you'll notice also that it didn't completely quit changing the numbers, but look what's going on down here. Like, oh, actually from here to here, nothing changed, but up here, there's still some change. Right. So this is the kind of thing I'm asking you to plot at least once to kind of show me that you're really getting to a local minimum. Once it goes dead flat, you got to a local minimum. There's no doubt about it. Right. And if it didn't get quite dead flat, that might still be good enough as long as it's pretty flat. Okay. All right, let's do this. While we're at this, let's do some other demoing. What happens? What do you think happens if instead of 0.1 for the learning rate, I make it, I don't know, let's try 1.0, 10 times bigger. How do you like that performance? Quite a bit worse, right? Maybe non-convergent? Maybe I'd have to get more evidence, but what if I make it 10? That's 100 times bigger than the initial value. Uh, See what happened? It's okay. Not okay. What happened?
Baby steps.
Yeah, steps were too big, starts oscillating. It didn't start that, this is only printing every 100 tries. So if you printed more, you might be able to see I would love to be able to actually let you see the data going up, the error going up, because you often can see it, and you're dying at that point. Let's try, let's try 5. No, still too big. All right, 2. Oops, oops. There we go, 2. Oh, really? But 1 worked. I guess 1 is right on the boundary of what can work. Back to 1. Wow, that really behaves non-convergently. How about 1.1? Oh, there we go. Look at this. From 0.6 to 1.8 times 10 to the 16th. Next, times 10 to the 32nd. You see? That's the picture I gave you on the board, right? I wasn't lying. He's just bouncing worse every time and then zoop, off to infinity. Okay? All right. Okay, so that's kind of fun. Let's go back and let's try to do something reasonable learning rate again. Maybe even let's try going smaller than we did before. Let's see how that looks. Okay, well, I don't know what that is. It looks like it converged almost immediately. Oh, I want to let me fix the model directory problem. Well, actually, let's fix it in a different way. Let's actually give it another name. I'll call it my neural net. Okay, so there it is. Okay, so in my directory here, I've got the old one I created. Here's the one I just created. Okay, now the next thing I might want to do is uh, test it against the held back data. That's this other pickle file over here, because there's a program to do that too. So that's Python test.py. I don't remember the options, so I'll just fail intentionally here. Okay, got to give the model dir. Let's say my NN. Okay, the test data, which you could start off by just testing on the data you trained on. Why not? Let's do that. Train.py. What's going on? What did I miss?
Against the big kind of people. PY. Yes.
Oh, trained up pickle. Right. Oh, there you go. Okay, it's just one number, right? So thanks for that. Just one number, which should roughly line up with this. Notice it's not identical. They might have trained a little bit more before it stopped. Okay. Oh, well, no. Yeah, it is the exact same data. Okay, now let's try against the held back data. Let's see. It's the numbers from the same source. How different could it be? Is it held or hold? Hold. Oh, right? Okay, this is that phenomenon you need to show me in your case that you are aware of this, right? Okay, I didn't train on this data. It's from the same source, but I still do worse. I didn't train on it. Okay, the next thing and last thing is this, that you might want to generate some images to see what's going on here. Okay, so I can do plot.py. I don't know the arguments. Let's just see. Okay, you got to give it a model dir. So that would be my neural net. And then a graphics file. Ping is a graphics format, right? Call it pick. Pick.ping. No, what did it do? Oh, I got them in the wrong order. Okay. Pick dot ping and then my neural net. Oh, what did I do?
Trying to open up the file that you give it. So you just need to run it one time, and then give it. It'll create a directory, and then you give it that directory and say pop this.
Well, I can't. I mean, I already just. I mean, I'm not creating a neural net now. Hang on. Let me try this one more time. I'm a little slow today here. Let's see. What is it saying? Okay, so we can't load. That pickle. Oh, it needs to know the data it wants me to plot too. Yeah, you've always yes. You always have to, okay, sorry. Yeah, it always wants to plot data. That's the way I coded it. So if you don't like that, blame me. Let me just do it without arguments again to see what it expects and in what order. Oh, the data file should come first. All right, so we trained this on train.pickle. So let's do that first. Okay, and then modeled my NN, and then pick.ping. All right, and then we can do the same thing and just plot against the held out data. Why not? Except we're going to need to give it another name. Pick2.ping. What's that? Oh, hold. Yes, you're correct. Hold. Right. And now if I want to see it, I think I got to pull it back to my computer, if I'm not mistaken. There are ways to open up graphics windows, and this actually is a great tool for doing it, but I don't do it every day, so I'm not gonna, and I have no time. So this won't be my learning day. So what you want to do is, what's that?
You have to select the file.
Got to select the file I want. Yes, that's right. Okay, so let's go here. Here's my class directory. Let's find my ping files. It's this one and this one. Let's see what happens if I just double click. We'll just download it. Oh, it downloaded and opened it. That's kind of handy. Okay, so right. Okay, does this output look like a reload unit to you guys?
No.
Well, I mean, it's got that linear unit after, right? So it's flipped, right? So instead of going up, it's going down, and instead of being kind of sharp up, it's gentle down. But yeah, definitely one. Yeah, that's one real unit, all right. Okay, and you can see as you put in, just go to 2 or 3 or 4, right? You can kind of see, it's kind of fun because then you can actually see the limits of the neural network. If you put 100 or 200, you won't be able to see that as easily, but you may get better performance fitting the data. You'll notice there's some noise in this data. Is it obvious to you all what the shape of that data is? It's amazing to me that in fact you can get anything out of that data, but you can. So I don't think this is an impossible problem. It's not impossible. It's just difficult. All right. And then let's check the other one. So we can see, let's see, what's distinctive about this thing? You see, we got a point way down here at 0, -1. Let's open up the other file and see if anything's notably different. So with the other file, the output of the network should be the same, but the data will be different. Okay, pick 2. And it loves making it tiny. Okay, see that one stray data point is gone. This is it. It actually looks quite a bit different. That's from the same source. So have fun learning from this quite uninformative data, but hard problems look like this.
We're not going to have to do any further sub-folding for the data set.
Unless you decide to do the extra credit, then you will need to split off some from your training set. Other questions? All right, we'll go back to lecturing tomorrow.
Lieutenant Colonel Black suggested Wednesday at 11 for a meeting time.
Okay.
I'm gonna ask him if he can do noon instead.
Okay.
But if he can only do 11, is it okay if Nick and I miss the first part of class for that meeting?
Yeah, I guess so.
We'll watch the video.
Yeah, that's what you'll have to do.
Thank you.
No problem.